So it will be presented by Jitin Jose. He presented the tutorial also yesterday on behalf of the Microsoft Azure. So today he will go into more details on MVAPICH2 on Microsoft Azure HPC. Dr. Jitin Jose is a senior software engineer at Microsoft. His work is focused on co-design of software and hardware building blocks for HPC platform and designing communication runtimes that seamlessly expose hardware capabilities to programming models and middleware. His research interests include HPC interconnects and protocols, parallel programming models, big data, and cloud computing. Before joining Microsoft, he worked at Intel and IBM Research. He has published more than 25 papers in major conferences and journals related to these research areas, and he received his PhD from Ohio State University in 2014. So Jitin, please share your slides and get started.
Thank you, Dr. Panda, for the warm welcome. And welcome everyone. So let me share the screen. So are you able to see the screen?
Yeah.
Okay, great. So yeah, let me start. So here is the overall outline of the talk. So we'll start with an overview of Azure HPC, the different HPC instances. And we'll talk about what are the unique challenges for HPC in cloud and how we address them efficiently. And we'll focus on the HPC software ecosystem, which includes MVAPICH2, MVAPICH2-X Azure. And we'll show some really nice performance results with MVAPICH2 and MVAPICH2-X on Azure. So yeah, so let's get started. And like always, also if you have any questions, please feel free to stop me in between, or we can go over after the talk. So yeah, here is a quick overview. So Azure HPC, so it's actually built on the three main pillars: high-speed networking, powerful compute, and seamless integration with the existing environment. So network-wise, for the HPC instances, InfiniBand is backend network. So we are the only public cloud that offers an IB, and like you all know, it supports all the OFA verbs, and all the IB-based MPI libraries are supported. So you don't need any special libraries or special designs to run on Azure. So whatever libraries that you runs on your on-prem cluster, you can still just build it and run there. So that's there. And powerful compute. So traditionally, when the cloud was started, the main use case was web applications, and we have seen over the past few years there have been a tremendous shift towards more HPC or AI applications, and now those become the forefronters. As far as different use cases. So we offer compute and compute optimized queues, storage optimized queues, memory optimized queues, as well as the GPU queues. And also another key pillar is seamless integration with the HPC environment. So you can have, say, some of the nodes on your on-prem cluster, and from there you can scale out to cloud as needed. So you have the cost effectiveness also in all the three aspects. So here are the a few of the HPC offerings in Azure. So broadly, we have two series, H series and the N series. So H series is basically compute plus IB. So H16R is one of the very first SKUs, supports FDR, and then we have the latest on that series is HB120RS v2. So here is a quick way to decode the name. So HB, and the first few alphabets, it's the family name, followed by the number of cores that are available in the VM. So for example, in this queue, there are 120 cores. And the R or S, so R indicates RDMA support, and S indicates premium storage support. So that's a and followed by the V2 or the V version. It's actually the version inside that family. And similarly, the N series, those are the GPU SKUs. So here I have included only the GPU plus IB SKUs, not the GPU only SKUs. So the latest in that series is ND40 RSV2. So here, this is an Intel Skylake based SKU, ND, with 40 cores and supports RDMA and premium storage. And it has 8 Tesla V100 like NVLink connected, and the backend network is EDR IB. Let's like quickly go over the unique challenges like with respect to performance and scalability for cloud and how we address them. So I mean, like like one of the main concerns or one of the main aspects is so you have some noise from the host OS or host hypervisor or the agents running on the host, and like that may impact your actual jobs running on the VM, right? So there have been like many like designs on how to approach that. So we'll go over our designs, and obviously you have to have a balance on the cost versus performance. So that's one thing. And the host interrupts, like say for example, for the communications, you can be if it's not good to have host interrupting in between, and which might reduce your performance to a great extent. And also we want to make sure the core and NUMA mapping is one-to-one, like whatever you have on the physical or bare metal side, if you're not exposing like one-to-one, it's actually not good, right? Like you'll see really random performance results or irregular performance results. And traffic from other customers, this is a shared environment, and there will be other customers running like workloads, memory, network intensive workloads running. So you want to make sure, okay, your workload that is giving constant performance, and you're able to get same performance over multiple runs, right? And there are also guest agents. So for example, like agents running inside the VM that help you say for example, some of the utilities, say if you want to reset password, you can do it from the portal, and the agent running on the VM will help you do that, right? So those agents are there, but you have to make sure you get the best performance even with those agents running. So here is how we address like most of the these issues. So a host VM partitioning. So here is how we design HPV2, the HPV2 SKU. So here, so HPV2 is actually based on AMD ROM, as you know, like it's a NUMA node, NUMA architecture. It's a SKU that has the NUMA architecture. So for example, there are 16 NUMA nodes in one socket. And each NUMA node, you can configure it differently, but in this case, it's 4 cores per NUMA node. And what we do is that we reserve 1 NUMA node per socket for the host. And we partition it using min root and CPU groups, so that, so the min root will prevent the host or any application that's running on the host to go to the VM cores. So it will be dedicated only on those two NUMA nodes. And similarly, CPU groups. Like the VM, the rest of the NUMA nodes or cores are reserved for the VM, so they won't try to land on the other cores. So there's a very clear boundary between these two cores. And here another thing to note is that these NUMA nodes are L3 are reserved in L3 boundaries. So there won't be any cache pollution between, say, host applications or host processes and between the VM ones. So there's a clear boundary between them. And similarly, the NDV2. So we take 4 cores per socket, and there also we can see a clear boundary, and we are able to get consistent performance across multiple runs. And another thing to note is that there is no hyper-threading on any of our HPC SKUs. And also we only have one VM per host. So the entire node is actually reserved for that VM. And all the cores are given to the VMs, all these VM cores. And as far as the network, so we offer the network using SRUV. So all the NIC features like are available for the VM. So for example, we have the CX5 and CX6 for the latest SKUs. HPV2 is ConnectX 6 with 200 gigabits per second. And these are like one of the features, like it supports DCT, hardware collective offload, UD-based multicast, hardware tag matching, so which Dr. Panda talked about in the morning. And reliability congestion control using Shield, adaptive routing, etc. And like we mentioned earlier, like there is only one VM per host, so only one VF is created, and that VF is given to the host, given to the VM. So there is no sharing between the device also. And network security. So InfiniBand has a notion of partition keys. So only the VMs which have the same partition key can communicate between each other. So by using partition keys, we isolate different customer traffic. And you can also have like multiple service levels within the same P key, but once you have the P key, like you cannot talk to anybody else. So that way we ensure network security in this case. One quick note here is that, so when you create this VM, you have to make sure that all the VMs are associated in the same availability set. I mean, there are deployment mechanisms that help you do this automatically. You don't have to worry, but just as a note, like make sure that all the VMs have the same availability set, or they are created under the same VMSS. And one of the quick ways you can check is you can just grep for the P key and make sure it's the same for all the VMs. And congestion control is actually one of the major issues. So, I mean, like I mentioned, like it is a shared environment. So there will be other workloads running. So one thing to note is that all the Azure HPC InfiniBand network is non-blocking, so there is no oversubscription. But if we just rely on static routing, it can still cause bottlenecks, because I mean the same path could be taken by two different communication paths, right? So it is still possible. So the solution there is adaptive routing, which is available on CX5 and later generations. So on Azure, so we have enabled adaptive routing on all the non-zero SLs. So if you want to take advantage of adaptive routing, just specify a non-zero SL, and you can take advantage of it. Like other thing is about NUMA mapping. So we want to make sure like there's a one-to-one mapping between the pNUMA and vNUMA and also the cores, right? So so this is so we make sure that that the mapping is actually one-to-one. So this is a quick example like, of how we see the latency metrics on HPV2. So here we can clearly see the NUMA boundaries. And so this is all, I mean, this is actually like the latency measured between each pair of cores. So we can see, okay, this is all within the first socket, and it jumps across the socket here, and similarly here. So we can clearly see the boundary, and this ensures that there is actually a one-to-one mapping, and it actually enables a lot of NUMA-aware designs. So you can do efficient process mapping. You can have like efficient NUMA-aware collective. So it opens door for a lot of like new designs. And HPC software ecosystem, like Dr. Panda always mentioned, like, I mean, even if we have the great hardware, like you still need to have the best software system to exploit the best performance out of it. So, so that's why we have the HPC marketplace images, and we have MVAPICH2 and MVAPICH2-X right there, so you can have your favorite MPI libraries there, and you can just spin up the VMs and start running your workloads, right? So you don't need any special configuration, etc. I mean, it's already there. So the CentOS HPC image it comes with Mellanox software. It has like all the IP-based MPI libraries, different HPC software libraries, and all the optimization configurations are recommended by by the different vendors. So, for example, in the marketplace, if you try to create a VM, it will ask, okay, what's the image that you want to use? You can just search for CentOS HPC and you can see the different VM images. And all the recipe here is actually marked in, hosted in an GitHub repository. So this is one option. The second option is you can, customers can just use the pre-built VM images or build custom image based on the image, or they are free to bring their own software stack. So all sorts of flexibility is possible. And MVAPICH2-X Azure. So Dr. Panda showed really nice numbers with MVAPICH2-X Azure in the morning. It's available in all the CentOS HPC images. These are targeted for Azure HP, HPV2, HC VM instances. And it has enhanced tuning for both point-to-point and collectives, XPMM support, DC support, cooperative rendezvous protocol, and hybrid RCUD support. And more details are provided in this blog post, so feel free to take a look at it. And let's take a quick look at the performance characteristics. I think we are slightly over time, but let's see. So the experiment setup, these were run on the HPV2 VM instances, and we used the CentOS 7.7 HPC image, which has the MVAPICH2 and MVAPICH2-X libraries, and Mellanox software 5.1 was used. So starting with MPI latency, so both MVAPICH2 and MVAPICH2-X achieves less than 2 microsecond latencies. So, as you can see, like there's magnitudes of difference comparing to like other cloud vendors. So, intranode, if you see, so because of XPMM, MVAPICH2-X actually gets really nice improvement for large message range. MPI bandwidth and bidirectional bandwidth, here also both MVAPICH and MVAPICH2-X achieves close to line rate. So both use the same protocol, so that's why we don't see much difference. One thing to note here is that so we used output rendezvous protocol for these experiments because that's what showed better numbers. And I believe MVAPICH2 team is actually putting that as a default for this platform. So MPI all reduced. So these are results with for OSU all reduce. So here we can see these benefit for the large messages are mainly due to the XPMM aware collectives. So around 3x improvement for large messages, and these were taken on 960 processes. So and if you compare these results with bare metal, they're like very close. So whatever the performance characteristics that you'll see on bare metal, you'll see on the cloud as well. And here is another really nice, important, a nice feature. So we ran GPCnet on HPV2. So like even Gilad was talking about GPCnet in the morning, like, and he showed really nice numbers. So we actually tried to reproduce that on the cloud, and this is what we saw. Like it's, on the left side, these are GPCnet latency, bandwidth, and all reduce for multiple iterations. So the y-axis here is the congestion factor. So you can see like it's sometimes it's about like 7x over the normal number, right? So which is not ideal. But with adaptive routing and congestion control enabled, like you can see like these are the different iterations of the same benchmark. So you're, I mean, close to 1 in this case. So these were run on 128 HPV2 VMs with 120 ppm, around 15K MPI ranks. And we used an upcoming firmware version, like it's going to be available on in September. So yeah, so that's, I mean, so this type of, congestion may not happen in real life, but the GPCenter, like it induces those things. But even with that, we see really nice performance here. And we also tried different MPI applications. So mini FE, like it's a strong scaling experiment. So, and we can see really nice scaling results here. We use the large problem size here, NX, NY, NZ equal to 1K. So we can see, and both MVAPICH2 and MVAPICH2-X seem to be showing similar results in this case. And this is again Cloudleaf, again with a really large data set. Here also really nice scaling numbers. So and we don't see much difference with between MVAPICH2 and MVAPICH2-X because this uses, doesn't use large messages for intranode transfer. So that's the thing. Yeah, this is WRF results. Thanks to MVAPICH team for collecting these. So here we can see really nice improvement for the 1K, close to 1K ranks. So this is again, the benefit is actually coming from MVAPICH2-X plus XPMM. So nice scaling factor. So, and then really nice improvement with MVAPICH2-X XPMM. So yeah, with this, let me conclude. So like we saw, with our design, we are seeing like very close to bare metal performance results. And with SRIOV, we are able to expose the network features. So whatever network features that are available on the CX5, CX6, we are now offering it inside the VM. And we have these out-of-the-box VM images with MVAPICH2, MVAPICH2-X Azure. So, you just need to deploy the VMs and you can get started. Like we saw, we saw really nice performance and scalability results on Azure. And we have, I'll also put pointers here. So please feel free to like go over in detail. So the first one is like these are some deployment scripts. So this is very easy. You just need to git clone, run say SHPC init, update a configuration file which says, okay, what are the compute instances that you need? What's the number of instances that you need? And save that file and do SHPC build. And you have your cluster ready. So that's one of the quickest ways to have your cluster. So we had a tutorial yesterday, so we have more details in there. So please feel free to take a look and take the other pointers. So with this, in the interest of time, I will conclude and happy to take any questions.
Jitin, there is one question in the QA box. You want to take a look?
Yeah, so Sharp V2 functional on Azure. So Sharp, the V1, it was not cloud ready. The main issue was that so Sharp, it has a dedicated resource, right? So it was, there was not a, it could cause like resource, there was no way to like clearly divide the resources between different tenants. So that was a limitation. But we have worked with Melnodes to bring that up in Sharp v2. Now on Sharp v2, like we haven't enabled that yet, but in the new HDR cluster, we'll be enabling that. Any other questions?
Yeah, I don't see any questions. Are there any other questions? On the Slack channel also, there is no question. So one quick thing, you showed those good congestion control numbers. Have you done any application level evaluation? I know these are the like latency bandwidth already is.
Yeah.
If you turn on the congestion control, do you see very uniform numbers for applications?
Yeah, so we had done some initial evaluations in the last SC. Like that was, I believe that was OpenFOAM, or I think that was Fluent. Yeah, so we saw really, and that was about 300 HPV2 VMs, and we saw really nice benefit with AR enabled, yeah, with AR enabled, yes. And I think we have a blog post also about that, showing the scalability and results there.
Okay. If you can just post that on the Slack channel, that will be helpful for the audience. Okay.
Sure, I will do that. Thank you.
Okay, so thanks then again. Thanks to Jitin.